Good morning, guys. My name is Virgilio Tijerina. I'm a senior student in the University of Texas, Rio Grande Valley, and today I'll be giving you a short presentation about the application of shape memory alloys in different fields, emphasizing its use in civil engineering structures. Maybe some of you are already familiarized with the subject of shape memory alloys, but for those who are not, shape memory alloys are unique materials that have the ability to achieve great deformations and to return to its predefined shape after unloading or after heating. It is a very straightforward concept. The material is basically allowed to undergo a transformation because of a process named Martin-Silic transformation. This Martin-Silic transformation can be produced by two means: changing temperature or by the action of stresses. As you can see in the diagram, it is a cycle. The materials go down to its twin phase, then stretch to form its shape to finally heat up again to regain its original shape. The first documented material with shape memory effect was a gold cadmium alloy in 1932, but the man who really ignited the spark was W.J. Buehler, who discovered the effect in a nickel titanium alloy in 1962. This discovery led to a boom in international research in the field and the appearance of the first real application of these alloys. Up to this day, the nickel titanium alloys are leading the industrial market, but the main drawbacks of these alloys for their application in civil engineering is the cost of production. But this could change in the future by the fact that new alloys with similar shape memory effect were discovered in recent years. These alloys are based on iron, which is way cheaper to replicate the effect. There are two groups of iron-based shape memory alloys. The first group contains alloys such as iron platinum and iron nickel cobalt, which exhibit similar characteristics to the nickel titanium alloys. In 2010, a variation of these alloys was presented. It recorded a recovery strength of 13% at room temperature and a very high tensile strength. However, these new alloys still need development to be able to produce them in large amounts for big scale elements such as civil engineering structures. The second group is a group of alloys such as iron, nickel, and carbon, and iron, manganese, and silicon. These alloys have received considerable attention over the past 2 decades due to their low cost, good workability, and good quality. Although the real applications are still limited, there are remarkable exceptions such as its use in large-sized joining pipes for tunnel constructions and current rail joint bars. The shape memory effect is commonly used in other engineering fields. This effect is present in couplings, actuators, and smart materials. Couplings are the first most successful applications, which were developed by the Viking Corp for an airplane company. Here is a cool mechanism that includes a shape memory coil spring in a thermostatic mixing valve. As you can see in the slide, this apparatus consists of a shape memory coil spring and a bias spring, which are opposing to each other. When the temperature of mixed water is too high, the shape memory alloy expands and the bias spring shrinks. Since the shape memory alloy spring is stronger than the bias spring, it results in a smaller opening for hot water and a larger opening for cool water. Possible applications of shape memory materials in civil engineering are passive vibration damping and energy dissipation, active vibration control, actuator applications, and utilization of shape memory effect for tensioning applications or sensors. Passive energy dissipation and active control represents two new innovative technologies for protection of structures under environmental loads. These technologies are being applied for the design of new structures or to retrofit of existing structures against wind, earthquakes, and other external loads. Damping stands for the conversion of mechanical energy to thermal energy and therefore for the ability to reduce movement or vibration of a structure. One main process for this is friction. either in the form of strong friction between parts of a damping mechanism or in the form of internal friction of the material of a damping part. As internal friction in shape memory alloys is comparatively high, they have a very good damping capacity. That is why it's a good option. Uh, Here, the Shimori alloy wire bays are installed diagonally in the frame structure, and as the frame structure deforms under excitation, the Shimori alloy base dissipates the energy through the stress-induced Martinson transformation or Martinson reorientation. The repairing of structures using the shape memory effect for pre-stressing tandems is a promising field for the use of iron-based alloys. These alloys have advantages compared to traditional pre-stressing technologies. For example, that there are no friction losses, no anchor heads, or no torques are required, and no space is necessary for applying the force with a hydraulic device. The reason is that the pre-stressing of the shape memory alloy tendons is not performed mechanically, as in conventional pre-stressing steel, but with heating. After the presentation, we can conclude that the use of iron-based shape memory tendons for the repairing of existing structures or the reinforcing of new structures is a promising field for the near future. Such iron-based shape memory tendons have several advantages, and another thing is that the cost of production needs to be lowered in order to increase the possibilities of seeing shape memory alloys in civil engineering structures. And this can be accomplished by not only using cheaper iron, but by finding new ways to replicate the Martinson transformation at a cheaper rate. Another thing is that more research is still needed to allow a better understanding of the material behavior, and that new alloys with fine precipitates have been developed during recent years and allow high recovery stresses without the need for thermomechanical training. Here is a video explaining or showing the shape memory effect in a shape memory alloy. Here the metal is being fitted out. And after going back to room temperature, the material recovered its original shape. Here's my personal information. If you have any question, feel free to contact me whenever you can. Here are my citations.